Hello, everyone, and welcome to this online edition of the AWS Summit. I'm Adrian Hornsby. I'm a principal developer advocate with AWS, focusing on architecture. In this session, I'll discuss some of the most useful principles for building continuously resilient applications. So buckle up, because I have a lot to share with you. So first, let me ask you a simple question. Do you remember your first outage? How smart did you feel back then and how confident you were? Well, I clearly remember mine, and I was really nervous. I was sweating a lot. My heart rate was through the roof. I just started to panic. I couldn't think straight. I felt very unprepared. It was a disaster. I had no idea what I was doing, and it took me an awful lot of time to figure out what the issue was, because I just didn't know where to start looking. And today it probably would take me only a few minutes to figure out or have a feel for what was wrong back then. It's always been a mystery for me why no one ever trained me, nor the school nor my employees. No one, really. I think I can speak for many of us. We get trained in production. So have you ever wondered why outages are so scary, by the way? So one obvious reason is cost. These are the estimation from IDC and the Potemkin Institute. And so how many of you would like to lose $100,000? Because that's the average price of an hour of infrastructure downtime. Of course, it's an average, but it's still very scary. And that puts a lot of pressure on businesses. Now, if you think about the previous outage we just spoke, how long did it last? Do you remember? And how easily it was to actually get to 1 hour of outage. So if you look at the anatomy of an outage, it looks something like that. First, you have the detection phase. Now remember that most of the monitoring tools, the alarms and escalation takes around 10 to 15 minutes to kick in. Then your team needs to evaluate what's going on. That's the debugging, reading logs, and trying to get a grasp of the failure at hand. And then it's response time, applying the fix, applying, patching the systems, things like that. And then it's recovery time. And often systems need to recover slowly and progressively to avoid the yo-yo effect, right? And finally, it's confirmation phase. And that's answering the questions, is the service fully back for all my customers? So 1 hour outage, trust me, comes very, very fast. And as you can see, I've also plotted the stress level during the different phases. Well, it's not a scientific plot because I never got to measure my colleagues' brain with some electrodes here. But that's how my colleagues and myself have felt for the past 20 years. Now, notice the stress level going up at the end. Why are folks scared in the confirmation phase when the outage is over? Well, that's because often that's when fingers are pointed. This is your fault, blame. And that's also when folks, the devs, the ops, the architects, the manager start to feel fear for their jobs. And what's the reaction to people and organizations when they experience fear? Well, of course, they want to avoid it. So many organizations lack confidence in their IT services and fear failures. They often believe that failures are preventable, and because they believe IT services are predictable. And they also believe that failure are caused by isolated changes. So these organizations often focus on maximizing the return on investment on the current IT services they have and actually resist change. These have led to the development of what's called robustness-centric risk management practices, and that's processes, controls, rules, change management. All that was put in place to limit the risk of future failures. So frameworks such as ITIL are a good example of frameworks that are optimizing for robustness. And these practices are often called risk management theater. And they are based on the assumption that preventive control on everyone will prevent everyone from making a mistake, or will prevent anyone from making a mistake. So these are some of the practices robustness-centric organizations put in place to reduce the risk of failures. And the problem is that maximizing robustness often leave organizations ill-equipped to deal with failures. So as explained in the paper, Resilience and Precarious Successes, when an organization optimizes for robustness, it usually underinvests in what's called the non-functional requirements, and that's monitoring, telemetry, infrastructure support, automation, and so on. It will be considered acceptable to do that because they think failures are going to be rare. Unfortunately, it's really naive to think like that. A production environment is a collection of unpredictable interactions happening in an unrepeatable conditions. It's a complex system in which the cause of an event can only be understood in retrospect, and that's often calls for the insight bias, by the way, that we'll talk a little bit later. Werner Vogels famously said, "Failures are a given, and everything fails over time." The truth is, a production environment is in perpetual state of failure. So Richard Cook explained in his book How Complex System Fails, and I quote, "The complexity of this system makes it impossible for them to run without multiple flows." And indeed, the fact that production systems often comprise hundreds of dependencies, the probability is so that at any given time, something somewhere is about to fail. We call that partial failure mode. Organizations that focus on robustness encourage an attitude that Sidney Dekker calls the bad apple theory. That's when the system is considered reliable except for the mistake that its bad employees do. So when a failure occurs, the bad apple theory that combined with the insight bias often produce a blaming culture, and that's really bad. The attitude and culture discourage learning and sharing and collaboration, and these are key practices for continuous improvement and thus key to resilience. So the question is, how do you trade the fear of failure for growth, opportunity, and improvement? Well, the answer, as you probably have guessed now, is by embracing failure and build resilience. And simply put, resilience is the ability for a system to respond, absorb, adapt to, and eventually recover from unexpected failures. In the book, Resilience Engineering a Practice, one of the Bible of resilience, the authors break down resilience using the conceptual model known as the 4 cornerstones of resilience. And first, there is the anticipation, and that's understanding what to expect, imagining potential failures, and attempt to mitigate them in advance. And notice I say attempt. Second is monitoring, observing operational condition, alerting when faulty conditions occur. Then there's responding. That's understanding what to do and how to respond when failure happens. And then there's learning. That's understanding why failure happened and deriving the best practices and recommendations, and then, of course, sharing them with the rest of the organization. So these cornerstones are non-linear, and they are interconnected attributes of resilience. And designing for continuous resilience means creating the environment in which the services that we build can gracefully respond, absorb, adopt, and eventually recover from unexpected changes, and especially recover from unpredictable failures. So I've listed here some what I've believed are the most useful principles for moving towards continuous resilience. I won't have time, unfortunately, to dive in every one of them, but I'll present some of which I think are critical or becoming to be critical. So let's take a look at developing our capability to anticipate. One of the most important parts of building a resilient system is reviewing and profiling our application code. Code quality is critical as quality impacts how safe, secure, and reliable our applications are. It's the foundation on top of which businesses are built. So continuously delivering high quality is critical for resilience. So code is considered good if it's if it does what it should, if it follows a consistent style, if it's easy to understand, if it's well documented, and if it can be tested easily. And while human-based code reviews are critical and mandatory, some tools are becoming essential to assist reviews and suggest improvement, especially now that complexity is growing. So Amazon's internal team have used code reviewers and profilers on more than 30,000 production applications. And between 2017 and 2018, and especially to prepare for the Prime Day, one of the biggest shopping day of the year, Amazon realized 325% of efficiency increase on CPU utilization and a whopping 39% lower cost. And that's using an ML-powered code reviewer and profiler. So code reviewers are important for each stage of the application lifecycle, both during the development and the deployment, and of course once the application is up and running. So the tool that Amazon.com used is publicly accessible to anyone by using the AWS console, and it's called Amazon Code Guru. It's powered by machine learning that provides intelligent recommendation for improving code quality and identifying an application's most expensive line of code. It scans for critical issues, identify hard-to-find bugs, and also recommends how to remediate them before they become outages in production. Now let's talk about some of the resilient application patterns important for us today. Whenever a service calls another one, failure can happen. This failure can come from the servers, the network, load balancers, disk, missing certificate, software operating system, and even mistakes from system operators. So anticipating this potential failure include designing systems capable of reducing the probability for failures. And of course, it's impossible to build systems that never fail, but there are a few things we can do to try to reduce the probability of failures. And you should employ these simple yet often forgotten principles. First, set the timeouts. Did you know that many of the frameworks we use today have default timeouts set to infinite? And if they are not to infinite, they are in the tens of seconds, minutes, or even hour range. This is hands down the most common failure I have seen. Second, you need to back off on retry. Not backing off is a sure way to end up with a retry storm or a subsequent cascading failure. And by the way, always set a jitter when you back off. Of course, you also need to limit retries, since by default the number of retries are often set to infinite. In some cases, I would even recommend to think about setting your max retry to 1. In most cases, 1 retry is enough to be resilient to intermittent errors. And more retries might do more damages to your system than good. So finally, limit the size of queues as well. Again, it's something that is often overlooked and led to the default values. On the backend side, the two most important tools for you, of course, are rate limiting your APIs and load shedding. If you want to learn more about how Amazon sets its timeouts and implement retries, I highly recommend this article from Mark Brooker, Senior Principal Engineer at AWS. Now let's talk about simple designs and constant work, because simplicity and having simple mental model is key to resilience. And let's use the widely popular Elastic Load Balancer as an example. So under the hood, the ELB runs on the AWS Hyperplan, which is an internal service embedded into the EC2 network fabric. The Hyperplan could handle a configuration change by using a workflow like this one. So instead, when a customer makes a change to their ELBs, the change is turned into an event and inserted into a workflow. And that is pushed to all the nodes on the Hyperplan. And then they could just simply ingest that change. Now, the problem with this push approach is that when there are a large number of changes all at once, the system is gonna slow down. More changes means more work. So when systems slow down, customers naturally retry, and then that slows down the system even more. That's not what we want. So the solution is surprisingly simple. So rather than generate events, the hyperplane integrates customer changes into configuration change that is stored into Amazon S3. This happens right when the customer makes the change. Then, rather than respond to a workflow, the hyperplane nodes pull the configuration change from the configuration file from S3 every few seconds. And this happens even if nothing has changed, even if the configuration is identical to what it was last time. That process keeps the load on the latest. The process keeps the load always the same. So effectively, the system is always processing and loading the maximum number of configuration changes. Whether the load balancer is changed, whether one load balancer is changed, or even if hundreds of them are changed, it all behaves the same. And the configuration file is also sized to its maximum size right from the beginning, and there are dummy configuration slots waiting to be filled with customer configuration. And that's called constant work, and it's one of the most critical ideas for building resilient systems. So storing the file into Amazon S3 and fetching it all over again in the loop, even from hundreds of machines, costs far less than the engineering time and the opportunity cost spent building something more complex would cost. Similarly, you can learn more about simple designs and constant work at how we do these at Amazon. And Colm McCartney wrote a beautiful article available on the Builders Library. Another design important in the anticipation of failure is limiting its impact, something called blast radius. Cell-based architecture is one of the best ways to contain that blast radius. Cells are multiple instantiations of a service that are isolated from one another. The service structure are invisible to customers, so each customer gets assigned one cell or several cells. This is called sharding customer, but nothing is visible from the customer point of view. So in a cell-based architecture, resources and requests are partitioned in these cells and they are capped in size. So this design minimizes the chance that a disruption in one cell affects the other. And by reducing the blast radius of a given cell within the service, the overall availability increases and continuity of the service remains. So for a typical multi-availability zone service architecture, a cell would comprise the overall regional architecture. Now take that regional design, and that's our cell. Then duplicate that cell and apply a thin routing layer on top of it. Each cell can then be addressed via a routing layer using domain sharding, for example, something that is very easy to do with Route 53. Using cells has a lot of different advantages, among which is workload isolation, failure containment, the capability to scale out instead of up, but more importantly, because the size of the cell is known and tested and very well understood, it becomes easier to manage and operate. So the limits are known and replicated across all the other cells. Of course, the challenge is knowing what size of cells you should use. Since smaller cells are easier to test and operate, while the larger ones are more cost efficient and make the overall system easier to understand. So the rule of thumbs that I like to use is to start with a larger cell, and once you grow, slowly reduce the size of your cell. And of course, automation is key for you. Now, let's talk about one of the most common reasons to failure, and that's mutability. And I will be upgrading a server to illustrate the problem. So upgrading a server goes something like that. So you log in, you stop the app, you update the repository, you do a library upgrade, test sometimes, debug often, and restart the app, and then you hope for the best. And during that time, the server and the system is, of course, down. So more often than rarely, these types of update results in failure, and then a manual rollback is initiated, and that rollback comes with its own risks. All these were and often still are standard practices. Less common practice, though, is to document those changes. So the solution to mutability is not processes or change management, but not doing the changes in the first place. And with the cloud, it's more and more easy. So put simply, the immutable infrastructure model is a model by which we update, we do security patches or configuration change outside of the production system. We don't do it in place. So if any change is needed, a new version of the architecture is built and deployed in production. So most common implementation of the immutable infrastructure paradigm is the immutable server. Now, it means that if a server needs an update or fix, a new server is deployed instead of updating the ones already used. And once it's deployed, we simply update the routing layer to route the traffic to the new version of the application. And this pattern also applies to containers and Lambda functions. So that pattern is actually called the canary deployment pattern and is used to reduce the risk of failures when new versions of applications enter production by gradually rolling out the change to a small subset of users and slowly making it available for everybody if no deployment errors are detected. So once the new version is deployed to all users, then you can slowly decommission the old version, but don't decommission it too fast. Sometimes errors happen after hours or days. So this strategy really minimizes the potential blast radius of failures and limit the impact to your customers, of course. Now, the benefit of the canary deployment for me is the near immediate rollback it gives you. But more importantly, it also gives you fast and safer deployments with real production test data. So the main challenge with canary deployment is the routing traffic between multiple versions of the application. So you can consider some of those routing or partitioning mechanism, internal teams versus external teams, paying customers versus non-paying customers, geographic-based routing, feature flag, or random. Note that this pattern is actually also the pattern that is used to deploy sales and one of the safe ways to deploy sales. So there are a few ways that you can deploy your application using canary deployment patterns on AWS. The three on the right integrates directly with AWS Code Deploy, which is a service that makes it easy to automate the software deployment. And because they are automated, they are more resilient as they can easily be stopped and rolled back if there are errors. So now let's talk about monitoring a little bit. As system becomes more distributed, methods for building and operating them are rapidly evolving. And that makes visibility into our service and infrastructure more important than ever. So Cindy Sridharan, author of the book Distributed Systems Observability, says that observability is a subset of monitoring, and that it provides not only a high-level overview of the system's health, but also a highly granular insight into the implicit failure mode of the system. In addition, an observable system furnishes ample context about the inner workings and unlocking the ability to uncover deeper systemic issues. And by the way, I highly recommend that book. It's phenomenal. There are three commonly agreed upon pillars to observability: metrics, logs, and traces. So the metrics are the numerical data measured at various interval times. So that's like request rate, error rate, duration, CPU, etc. Then you have the logs, that's the timestamp record of discrete events that happen within an application or a system, such as a failure, an error, or a state change. And then the traces, and the traces represent a single user's journey across multiple applications or several services. While there are quite a few tools that can help you with observability, It's worth mentioning that we recently launched in preview the AWS distro for OpenTelemetry. And that's a distribution of OpenTelemetry project that lets you instrument your application to send correlated metrics and traces to AWS or partner monitoring solution. So while all the services represented in slides are very critical to observability, one in particular is helpful when it comes to resilience and especially recovering from an outage. And that's Service Lens. Service Lens lets you easily correlate the logs, the metrics, and the traces to quickly identify service bottlenecks. And this integration is key to resilience since you don't have to go back and forth between different tools, and thus your focus and attention is kept on the issue at hand. Now, let's take a look at responding to failures. So, as John Alspo said, being able to recover quickly from failure is more important than having failures less often. And this could not be more accurate. Now, recovering is not always a binary solution. Remember that we talked about that earlier. Production systems often comprise hundreds of dependencies or services. Some are more critical than others. So from a recovery perspective, it's extremely important that you define what are your dependencies and services criticality. And from that, derive what are the different operating modes that you have. At minimum, you need to define your normal operation mode and your minimum critical operation mode. And of course, you can have lots of different levels of criticality, but it's the bare minimum to start with. For each mode, you can then work out a different recovery plan from short to long term. So while this seems trivial, it's often not implemented. And then during an outage, you end up with unfocused operation, unorganized and inefficient team, resulting in prolonged outage. So as we talked about earlier, automation is a critical part of resilience. But automation is not only for deployments, and it's also an important pattern for responding to changes. Leveraging this pattern lets your architecture react to in response to events. And an event can be a change in state or an update, or worse, a configuration change. Remember our immutable pattern. So for example, here is a simple pattern that responds to a change in the S3 bucket configuration. And if a change event is triggered, it reverts and reapply a strict configuration. So if your S3 bucket was initially private, and if there's a change that makes it public, then there is an automatic response that makes the bucket private again. As you can see, the event-driven pattern is an extension of the immutability pattern and is something that you should really put in your toolbox. And to hit the nail on the head here, mutability is one of the most critical attack vectors for cybercrimes. So when a bad actor attacks a host, most of the time it tries to modify servers, do some change in the configuration file, open some network ports, replace libraries, modifying libraries, or even inject new code. So a change means that the architecture is compromised and it should be isolated and replaced immediately. And for me, that's DevSecOps at its best. Detect, isolate, and replace. A big part of resilience is also being able to respond efficiently. And this is something that machine learning has become more and more useful with. Informed by years of operation at Amazon and AWS, we've recently launched DevOps Guru. And that's a machine learning powered service that makes it easy for you to automatically detect issues and improve your application's availability. And of course, reduce extensive downtime. Now, this sort of ML-powered tools are gaining popularity, and for good reason. They help us reduce the noise, brings to surface some of the critical and relevant data that we not necessarily would have seen, and it helps identify the cause of failures more quickly. And in turn, it really minimizes the time to recovery. Finally, let's take a look at how we can best learn from failures. One mechanism that is critical to continuously improve resilience is something that we call at Amazon the correction of error. It's very similar to a postmortem. It's a process where the team reflect on the problem, maybe an unexpected loss of redundancy or a failed software deployment, anything like that. And then we document what the problem was and how to avoid it in the future. So there are 5 main sections in the COE document. First, what happened? What data do you have to support your analysis? What's the impact on your customer? What are the contributing factors? And what did you learn? And especially, how do you prevent it from happening again in the future? And we use this mechanism to learn from mistakes. So whether there are flaws in tools, processes, or the organization. So the COE mechanism is critical to identifying contributing factors to failures, and more importantly, to drive continuous improvement. So to learn more about our COE process, you can check one of my favorite reInvent 2019 session from Becky Weiss, who is a senior principal engineer at Amazon. And finally, I want to talk about chaos engineering, because continuous resilience would not be possible without talking about chaos engineering. So chaos engineering is a process of stressing an application and testing in testing or production environment by creating disruptive events such as a server outage or an API throttling, and then you observe how the system responds, and especially you then implement improvements. And you do that to prove or disprove your assumption about your system capability to handle disruptive events. So chaos engineering helps improve the resilience and performance of your application by uncovering hidden issues and expose monitoring, observability, and alarm blind spots. But more importantly, and I think what is critical to resiliency, is chaos engineering practices gives the organization a platform to perfect the operational skills. Remember when you have an outage and you don't know where to start? Well, chaos engineering gives you a platform to learn how to react to outage. And that skill is critical to building a culture of resilience and especially improve recovery time from failures. Now, to help you get started with chaos engineering, we just recently launched AWS Fault Injection Simulator, AWS FIS, which is now generally available in all commercial regions. And that's all for now, folks. One important thing to remember is that change takes time. So don't lose your patience and trust the process. There's no secret sauce. The real quality is how to achieve high quality is based on habit and paying attention to detail, being paranoid with what could go wrong, and consistently strive for improvements. So I have included a bunch of resources for you to keep learning about the process of building resilience. And you can also check our AWS training and certification focusing on DevOps at aws.training/DevOps. And thank you very much for your time, and I wish you a great end of your day. And I almost forgot, please remember to complete the session survey. That helps us improve. Thank you very much. Bye-bye.